I don't know if you saw, there is a Mythbusters episode in which the guy dips the hand in molten tin. It's all about this, right? And a combination of something else that we're going to see in a couple of weeks. The guy gets the hand wet. When puts the hand, the water evaporates and makes an insulating layer of water vapor, which being a vapor is quite insulating, right? We're going to see all that stuff when we talk about phase change. But so boundary layer. And this is our introduction to convection. Actually, I should better say this. Convection. Right, this is chapter 6 in the book that nobody reads. But anyway, that's the reference for you. And we're going to be based on boundary layers. How did it work? How do I calculate heat flux by convection? Thank you. Thank you. Right, this is what we have been doing so far. And then I told you, this is a lie, right? But it's so convenient that everybody uses it. Okay? And funny enough, the Mechanical Engineering magazine had an article in the last issue saying why H should be abolished. Anyway, crazy guy. But it's true that it is a lie. What is the truth? Well, the truth is that in reality, Q of convection is Q of conduction on a boundary layer. This I said to you before, right? Is through an insulating blanket, right? And in this case, it would be minus K dt dx on the surface, right? And this dt dx is the temperature gradient through this insulating blanket, right? So what we said is, if you remember how we like to define things, we can say this is K times T infinity minus Ts over Y, and I'm going to introduce a new term, YCT, right? I'm going to tell you soon what YCT is, right? Anybody can give me a suggestion of what this YCT would be, just from seeing that symbol is in the equation. Thank you. Who said that? Whoever. Awesome. Thank you. Thank you. Fills my heart. Rainbows and puppy dogs. Okay, good. This is awesome. That's exactly what it is. So again, like the notation sometimes gets clunky. I don't like YCT. I would like to use delta, but delta is taken by others. So what are you going to do? So here we have now a surface. For example, this could be the hand of the poor guy getting the blisters. Huh? Right? Now, I want to talk about what's happening outside, not inside. Everything we have been looking so far is what happens inside your body. Now I want to talk what happens outside. Outside in the fluid. Outside in the boiling water. Outside in the air or the gas or whatever. The fluid that is outside. So this is the surface. And I'm going to use this coordinate axis now. And everybody uses this one, so I'm going to stick with it. This is going to be the x direction. And we don't do this to confuse you. There are good reasons to call this direction x, right? But if you remember, we used to call x the one coming into it for semi-infinite solid, and x was the one coming from the middle of the wall for spatial effects, right? So funny, right? Who's x, right? He's schizophrenic, doesn't know what it is. But okay, so, and this is going to be y. And here we have this insulating layer, right? And this is the YCT. I'm going to make the graph now. And this is y. here we have T infinity, right? So here we are going to have T infinity. Here we're going to have T surface. And this is what this YCT looks like. Here's YCT. So I'm going to erase here. The book does not use this notation. And some books use they mention this concept. So YCT is, some people call it conduction thickness. And the reason for this funny notation, remember when we characteristic length, we would call it XC, or characteristic time, we call it TC, right? So this is a characteristic length in the Y direction. And then we're going to see sometimes the characteristic length can be for temperature. That's why we have a T. Some other times is for velocities, for the viscous boundary layer. So Y is because we're in the Y direction, that is typically the one we use to measure perpendicular to the wall in convection. The C is because it's a characteristic value. And the T is because it's for temperatures. All right, horrible notation. I would love to call it delta, but it would confuse us. Now, look at what I did. I said that the temperature in our boundary layer has this kind of shape, right? That looks like an exponential decay again. And of course it's not. Something else, but looks awfully like an exponential decay, right? And we're going to see, what I'm going to show you today, is that in some cases, this curve, you know what it is? Is the complementary error function. Isn't that funny? Because that's exactly what we were doing with the semi-infinite solid. Right? And now you realize that this is exact because I'm defining my YCT using the slope, right? So this concept of YCT, right? This conduction thickness makes this calculation, this is exact. Because that's the way I define YCT. Let's look at this. So if I combine this with this, right, what I'm going to get is, yeah, I think I did it right. Yeah, that's right. So if I combine one with the other, I'm going to get that combining equations. See? Yeah, that is minus T infinity minus K. Thank you. Thank you. So if I combine equations, right, I am going to end up having that that this YCT is K over H. Right? Or I could say H is K over YCT, right? However you like to see it. But I want to draw your attention to something. If I know the fluid that is outside, the K of air, the K of water, or the K of whatever it is, all I need to know to calculate H is the thickness of this boundary layer, right? And this becomes a fluid mechanics problem. So we already did this. I would like to do it again. So for forced air, right, that would be the convection coefficient when we have wind, right? K is 0.03 watts per meter Kelvin. H is more or less 100 watts per meter square Kelvin. These are ballpark values we've been using all along. And this gives us YCT, right, equals 0.3 millimeters. But this is not just like this is not just about the calculations. Let me show you this. This is a problem from an old exam. It's pretty cool because if you know the convection coefficient, you can calculate how much you can overclock your chip. Do you know that the limit to overclocking your chips is heat transfer? It's not electronics. Do you know that? In this problem, if you see, I said, assume there is no interaction between the pins. I said assume there is no interaction between the pins. What I want to ask you is it true? Actually, it is true, because the distance between the pins, this is 3 centimeters, and we have 1, 2, 3, 4, 5, 6, 7, 8. What is 30 millimeters divided by 8? Whatever it is. The distance in there is bigger than 0.3 millimeters, right? So the boundary layers don't interact with each other. So of course, the problem is, imagine you put them too close to each other, the boundary layers impinge, right? And then then you have just conduction there. You don't have convection anymore. You see what I'm saying is, on a surface, this could be the surface of the pin. Here is the air flowing freely. But here, the air is moving very slow, right? And has this insulating blanket. Now, if the pins are too close to each other, if the pins are closer than 0.6 millimeters, right? The two boundary layers would merge into one conduction thing. We don't have a boundary layer anymore. This is very, very important. This is the way you calculate, for example, in a air-cooled motorcycle engine, the BMW, the space between the fins is such that the boundary layers don't interfere with each other. You would think that if you put more fins, you cool more, but it's not true. If you put enough fins, you have no room for the air to go and becomes a solid again. Now, if you have too few fins, the air moves fine, but you don't have enough fins. So you want to put as many fins as you can without impinging on the boundary layers, right? These insulating blankets. There is something else that is interesting. This concept of an insulating blanket makes sense when the boundary layer is thin. What do I mean? This BL stands for boundary layer, right? Is thin. For example, imagine I have this body and I have this boundary layer here. If I were to have this solid and here some convection, yes, this is okay. But if I were to have this little ball and the boundary layer was thick as this, you know what? Do you think this is a convection problem? This, in reality, if all this part is like having this little hot, like ball bearing inside molasses, right? There's no real convection. There's no motion. This is a conduction problem, right? You follow what I say? One thing is to have a thin layer of insulation, so you assume the body is the same, right? It just has something on the surface that is kind of insulating it. But when the whole insulation is bigger than the body, then it's a different story. You have a conduction problem now, because here, the motion of the fluid inside the boundary layer doesn't really matter, right? It's just conduction in there. We're going to see when we look at the correlations say that when whatever parameters make the boundary layer be too big, the problem turns into a conduction problem. So this concept gets interesting because brings us to an important parameter we're going to be using a lot. So So we're saying that this YCT, this thickness of insulating blanket, has to be thinner than the size of our body, whatever, length, width, or something like that, something that defines the characteristic length. Of course, we're going to see exactly what to use in formulas. If I write it like this, this is one of the criteria. Okay, little by little, let me show you this. If I do LC over YCT, this is LC over, we said YCT is K over H, right? Now, HL over K. Does it sound familiar to anybody? It sounds like a Biot number, right? Okay, but thank you. You said it half right. Now it's called the Nusselt number. Who knew? And this seemingly small difference is actually enormous. Because in the Biot number, right, when we do K, what is K? Of course, thermal conductivity of what? For the Biot, is the body. Is the body. We're seeing how the heat is being conducted inside the body. This K now is the K that was associated with the fluid. Right? So this K is for the fluid. And there's something else. In the Biot number, typically, the characteristic length is the length in which you are moving in the direction of the motion of the heat. Right? In a sphere was the radius of the sphere, and a wall was the thickness of the wall. Right? In a cylinder was the radius of the cylinder. But this is, and now not anymore necessarily in direction of heat flow. You're going to see, for example, that L now for when we do the Nusselt for a wall, it's going to be the length of the wall or the height of the wall, not the thickness of the wall anymore. So it looks the same. It's not the same at all. It's so seldom Nusselt and Biot cross paths. So seldom. Let's do one sanity check here. So, example, right? 1 meter tall window. Right? Let's say H for that would be more or less 10 watts per meter Kelvin if it is an indoor window. Right? That corresponds to stagnant air. And K for air is 0.03 watts per meter Kelvin. So if we do the Nusselt in this case is the Nusselt in this case is H is 10 watt per meter Kelvin. L is 1 meter. Right? You see how this is different than before? For the Biot number, the question was how thick is the wall? Now we're asking how long is the wall or how tall is the wall is. And over K. And this gives us 333. So this Nusselt number, that is something new that just appeared, it's a new concept. This Nusselt number is the way in which the convection coefficient is typically expressed in books, in tables, in experiments. And it has to be a large number, right? We already said has to be much bigger than 1. Look at one typical case for a window, 300. Yes?
Isn't it 10 watts per meter squared Kelvin?
Yeah, didn't I put it? Yeah, thank you. So, okay. So, the whole point, what we're going to see, and one of the concepts that is important for your exam on the quiz 2 on Friday is convection is all about calculating the thickness of the boundary layer, of the insulating layer, right? What is called the thermal boundary layer, right? That is what it comes down to. You're going to see lots of tabulations. You can run through those tabulations blind, and they will never make any sense to you. What I hope to do here in this class, you can read the formulas. You don't need me to see a formula and plug and chug. But what I hope is that if I do a good job at explaining this boundary layer concept to you, many things will start making sense to you without math. And some of those might even let you do calculations with real numbers without needing to go for the tables. Okay, so calculation of H is essentially a calculation of this thickness of the boundary layer, right? Now, inside this YCT, inside the insulating blanket, we have conduction. Outside the insulating layer, we have advection, right? We have this motion of fluid. But inside, we have conduction, as if nothing was moving, right? So this comes to fluid mechanics, right? So we have inside YCT, we have conduction, as if there is no much fluid motion, right? And outside YCT, we have advection. So we have a fluid mechanics problem. So when you took fluid mechanics, all of you did, you were exposed to at least to the words of boundary layer in fluid mechanics, right? Okay. In fluid mechanics, there is a boundary layer. And then in heat transfer, there is another boundary layer. This is the funny thing, and this is an important thing that for me was not intuitive when I first came across this. Why isn't there a single boundary layer, right? And I'll tell you right now, in intuition, in words, and then we're going to do it for real. This is what happens. In the thermal boundary layer, that is given by how much the heat can diffuse in, right, our fluid. So, as you can imagine, a metal that has very high thermal diffusivity can diffuse very quickly and have thick thermal boundary layers. Oil, on the other hand, is not a good thermal conductor, but is very viscous and can develop a viscous boundary layer very quickly, right? So these issues of viscosity versus thermal diffusivity give you two different boundary layers. In some cases, they are very similar, but in some cases not. In some cases, the viscous boundary layer is way bigger than the thermal boundary layer. That's the case of oil, for example. Some other cases, the thermal boundary layer is way thicker than the viscous boundary layer. For example, in the case of molten metals or plasmas. So before I get into the thermal boundary layer, before I do that, I'm going to show you a short video about the viscous boundary layer that was done, I don't know, in the 50s. So let's see here.
Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present.
Okay, attention to this. Do you see how the fluid gets stuck on the surface of the plate? That's called the non-slip condition. Extremely difficult to violate, right? Rumor has it that some fish can do it. There are experiments trying to put slime on submarines to break this non-slip condition, and that way to be faster. Okay, don't worry about that. We have the non-slip condition here in this class, all right? And pay attention how the thing gets stuck there as if it was molasses. But this can be water, can be air, can be anything.
In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected.
So you see what it said. Inside the boundary layer, viscosity dominates. Outside the boundary layer, there is no issue of viscosity. It's as if thing was just, there was no plate, right? That was a huge discovery. People discovered this, Prandtl discovered the boundary layer about 100 years ago, right? And was such an earth-shattering thing because if you write the equations and then you do the experiments, they would not match because they were simplifying, saying the flow as having no viscosity, and they were getting zero drag. Was a big thing, this concept of boundary layer, when it happened.
The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth.
Now they're moving the plate. What I want you to see here is how the boundary layer gets thicker as the time goes by. Right? The boundary layer is going to get thicker as the time goes by, but it kind of gets thicker fast at the beginning and then kind of doesn't grow so much later on.
The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer.
So the point here is I just showed you something that you should know from fluid mechanics, but I wanted to bring it up. How this thickness of the plate, right, increases with time. And there are two ways you can look at it. So you can look at it at a given position, and with time it gets thicker, or you can keep tracing the fluid, right? And it's more or less the same because the fluid is moving at a constant velocity, the far away fluid. So as you say, longer time means longer distance down the plate.